Using logarithmic differentiation, we can differentiate functions that would otherwise be horrific to do so, or that we can't do using techniques we've seen so far. Here's an example. Y equals e to the x times the cosine squared of x divided by x squared plus x plus 1. I'd like you to think about finding this derivative using the product rule, the quotient rule, and the chain rule. It would be terrible. So what we're going to do is use properties of logs to simplify our work. And in order to use properties of logs, we have to have logarithms to begin with. So we're going to apply the log to both sides. So we have natural log of y equals the natural log of e to the negative x times the cosine squared of x divided by x squared plus x plus 1. Our properties of logs say that I can turn a quotient into a difference. Further, I can turn a product into a sum. And so applying those two, we can write that we have the natural log of y equals the natural log of e to the negative x plus the natural log of the cosine squared of x. Now that's from the numerator. And then minus the natural log of the quantity of x squared plus x plus 1. That minus is because we have a quotient, right? So that would be from the denominator. We have a further property of logs that says that an exponent can come out front as a coefficient. So for the natural log of the cosine squared of x, we can write 2 times the natural log of the cosine of x. Well, I suppose we can do that for e to the negative x. We can pull the negative x out front as a coefficient. We end up with negative x. But since what's left is the natural log of e, that's all we end up with for that term. For that term, we also could have used a cancellation property of logs, right? Anyway, we end up with the natural log of y is equal to negative x plus 2 times the natural log of the cosine of x minus the natural log of the quantity of x squared plus x plus 1, because there's nothing that can be done about that, those three terms inside of a log, right? Our properties apply to products and quotients, not to sums and differences. Now this was the goal of using logs. Using properties of logs, we have now made this expression, we've expanded it, but we've made each term as simple as possible. Sometimes folks try to do this, they apply the log, and then they still use a quotient rule or something. I'm saying, don't do it. Wait till you have everything, each term, as simple as possible. Now on the left-hand side, we're going to differentiate the natural log of y, but we're going to differentiate with respect to x. That means implicit differentiation. So we have 1 over y prime is equal to, then on the right-hand side, negative 1 plus 2 times the derivative of the natural log of the cosine of x. That's going to be 1 over the argument, so cosine of x in the denominator, times the derivative of the inside function. The derivative of the inside function is negative sine of x. We're going to do the same thing in the next term. The derivative of the natural log of x squared plus x plus 1 is going to be 1 over the x squared plus x plus 1, but instead of putting 1 in the numerator, I'm going to put the derivative of the inside function, and so 2x plus 1. I'm going to do two things in the next step. First, I'm going to isolate y prime by multiplying both sides by y. So y prime is equal to y times negative 1 plus, nope, because the other thing is I'm going to simplify this to negative sine of x over cosine of x. That's going to be negative 2 times the tangent of x. So we have y prime equals y times the quantity of negative 1 minus 2 times the tangent of x minus 2x plus 1 divided by x squared plus x plus 1. And we're almost done, but not quite. I do have y prime by itself. I wanted that. But I have this y over here as a factor in the answer, and I don't want y prime and y. That's a whole different kind of equation. So let's go back up here. Y originally looked like e to the negative x cosine squared of x over x squared plus x plus 1. So y prime will then become e to the negative x times the cosine squared of x divided by x squared plus x plus 1 times the quantity of negative 1 minus 2 times the tangent of x minus 2x plus 1 over x squared plus x plus 1. That turns out to be our derivative. You may look at that and say, that looks hideous. I agree. It's not going to get any prettier, but imagine trying to do it using previous techniques.